Oh, I needed a pair of rulers. Hello, welcome to the second part of lecture 1. I'm just going to complete a few minor points related to analog to digital converters. Now, if you go back to the chart I showed you in the previous lecture, we consider the various types of ADC. This is what we need to remember. There's 4 basic types: the dual slope ADC, successive approximation, a flash ADC, and sigma delta. The dual slope, this is the one that slowly charges up a capacitor with our unknown and then discharges it with a known, and if we measure how long it takes to discharge, then we have a measure of our unknown voltage. Successive approximation, this uses a reference voltage that's divided down in binary values, and we try those voltages out in turn, slowly approximating to our unknown until we get the result. A flash ADC, very expensive, very fast, lots and lots and lots of comparators. Every one has been set to each of the possible results, and we get a near instantaneous conversion of our unknown voltage. Finally, the sigma delta, this is a device that uses a very long counter, usually 24 bits, and that tracks up and tracks down, trying to follow what the unknown voltage is. And therefore the contents of the counter itself will be the unknown voltage. In terms of speed, the slowest is the sigma delta, typically 1 or 2 conversions a second. Next we get the dual slope, maybe 1 to 30 conversions a second. The SAR, we get 1,000 conversions to 10,000 conversions a second. The flash ADC, this runs at megahertz. So you tend to use these devices for video, high-speed data acquisition, military applications. Most industrial processes use a SAR type device. The dual slope is used where cost is an issue and speed isn't so bad, 1 to 10 hertz. That's usually enough conversions for most non-critical control applications. Sigma delta, very, very cheap, very, very low cost, used in domestic environments, domestic white goods, high volume, low cost. And again, here we see the idea of the cost from the most expensive flash through to the SAR, dual slope quite reasonably priced, sigma delta virtually free, very, very low cost. And again, consider the noise immunity. The dual slope is the best for noise immunity. SAR is very poor, and so you'll have to use some digital signal processing to improve the signal to noise ratio afterwards. The flash ADC is quite good because it's normally converting data faster than the noise is actually arriving. And the sigma delta, it's so slow the noise hardly impacts on it at all. So here we have our basic chart and how they operate. But one of the requirements that you will have is that you will have to select as the programmer the specific particular characteristics of the ADC. And there's 2 key characteristics that is your job as the programmer. How fast does it convert? And how many bits in the resolution do you require to get the value you want? Now consider first, how fast does it have to convert? Now somebody's trying to steal my lunch here, and I'm not too happy with that. But how often do I need to check how quickly the frog is coming to grab my lunch? Think about it. If the frog moves very, very slowly, I only need to check very slowly. So the speed at which I need to sample the scene is based upon how quickly the scene moves. If the frog moves very quickly, I've got to keep looking very, very quickly. There's a direct relationship between the sampling rate, how quickly I look to make sure it's not going to steal my lunch, and how quickly quickly it moves. If the object is moving fast, if we have an extremely fast process, if we're driving very fast, if we can accelerate very fast, we've got to look very quickly to see what's going on. On the other hand, if it's moving very slowly, we don't need to sample as fast. Now, what's the advantage of that? The slower the sampling rate we can get away with, remember the cost of our devices, the slower devices were cheaper. If we can get away with a very slow sampling rate, then we can use a cheaper device. And also, in fact, there's a lot of other advantages. The software is easier, the parallel processing is simpler, lots and lots of things are simpler. But is there a relationship that we can write down? Well, there is. There is. And the logic is quite simple. The faster an object is moving, the quicker we need to sample. The slower it's moving, the slower we need to sample. So there clearly is a relationship that we can start preparing. And we can say that the sampling rate is proportional to the maximum rate of change. The maximum rate of change. Let's put that on our board because we're going to come back to that equation, and it'll be much easier if we start building up this equation. It's a very simple relationship. The sampling rate is proportional to the maximum rate of change. The faster our system is changing, the quicker an object is moving, the faster that the frog is arriving to grab my lunch, the quicker I've got to look. The slower it's moving, the slower I look. So here's part of our equation. But there's something else we need to take into account. This isn't the full story. How precise do we need to know the precision of the object? This is the other thing that we have to take into account. Now let's return to the frog. Now, at the moment, the frog is in a quite safe position. It's a long way away from the lunch. The distance is a long way. When do I need to know there's a problem? Is that a problem? That position? Or that position? Or that position? Or that position? The finer the resolution I need, the more often I need to look. So, regardless of the speed we're moving, this is irrelevant to the speed. If I want to know where the frog is precisely to a position of 5 millimeters, moving at that speed very, very slowly, I've got to look very, very fast because it was moving 5 millimeters at quite a rate. So if I want to know whether it's here, or here, or here, or here, or here, that's speed independent. That position, the speed at which I have to sample is totally determined by the precision. I've got to look very, very quickly. However, if I'm only interested in whether the frog is here or here, I only need to look then and then, very slowly. The actual rate of change is the same, but because the precision is wider, I don't need to look as often. It's like adjusting the steering wheel of your car. If you are quite content, you're going straight along, and you're driving along, you only need to adjust occasionally. But if you're going around a bend, even if it's at the same speed, you should be taking more care and thinking more about it. So there's another issue we have to take into account when determining the sampling rate. And that is, how fine is the resolution of our measurement? And that is known as the minimum resolvable value. It's no longer a proportionality. That actually is the solution. The sampling rate of our ADC is equal to the maximum rate of change divided by the minimum resolvable value. So the faster an object is moving, the faster we have to sample. And the finer the resolution we require, again, the faster we have to sample. Now these are parameters that you would derive from the specification of your real-time system, from which you derive the sampling rate, and we must stress that is the minimum sampling rate. Really, you've got to go as faster than that, usually a factor of 10 to be safe, but you've got to go faster than this minimum value, and that's how you derive it. And from that, you can decide which of the classes of ADC are suitable for your application, and thereby you will choose the right device. Now let's do a sum, just to show you how this works. Let us assume we are trying to control the temperature of a blast furnace, a Bessemer converter that's converting iron ore to steel. A very common everyday process, maybe not for you and me, but there are steel conversion plants everywhere in the world, and it's an important natural resource. Operating range of those sort of systems, typically 300 degrees Celsius up to about 1500 degrees Celsius. That is the total range of the thing. How precisely do we need to measure it? Well, normally within about 10 degrees Celsius is more than adequate. So we say plus or minus 5 degrees C. That is our resolution. What is the maximum rate of change? How quickly does it rise? Well, I'll choose a value out of midair. Let's assume we can raise the temperature of this system by 100 degrees Celsius in 1 second. These are fictitious values. A Bessemer converter won't run that fast. I'm just choosing these values for the purpose of this illustration. So our operating range is 300 to 1500 with an accuracy of plus or minus 5 degrees. We can increase our temperature by 100 degrees in 1 second. If we need to monitor the temperature, what is the minimum sampling rate required for our ADC? So the maximum rate of change here is 100 degrees per second. So that is 100 divided by the minimum resolvable value is plus or minus 5, so that's a 10 degree accuracy, divided that by 10, so that equals 10. The units are hertz. The minimum rate at which we have to sample the temperature of our steel converter is 10 times a second, or 10 hertz. Therefore, we can use a dual slope ADC, reasonably low cost. How do we derive that? You get it from the specification. You've got the operating range. We'll come back to these values. We'll use these values again in a moment. The operating range. The accuracy, plus or minus 5 degrees, so we have a resolvable value of 10 degrees Celsius. The maximum rate of change I've given you, you can raise the temperature of the converter by 100 degrees C in 1 second. The question is, what is the minimum sampling rate for the ADC? Go to the equation. The maximum rate of change is 100 degrees per second. There's 100. The minimum resolvable value is 10 degrees. Divide through by 10, and you get a sampling rate of 10 hertz, or 10 times per second. And that is the minimum. It's a very simple rule, a very simple equation that you need to remember. So let's just remove that, and we'll move on to another issue related to ADCs. How many bits do you need in the ADC to get the correct answer? What is the resolution? All of these, the computers can think of numbers in terms of bits, binary numbers. So if you had 8 bits, you could think of a number between 0 and 255. If you had 10 bits, you could think of a number between 0 and 1023. How many bits do you need to resolve the value you want to read in the real world, the resolution of our measurand when it finally hits the computer. This is quite important, because the more bits you have on the ADC, the more expensive they are. If you can get away with an 8-bit ADC, they are extremely low cost. 10 bits, fair price. 12 bits is quite common. You go over 12 bits and you're adding zeros onto the price of that component. 14 bits, 16-bit ADCs, very, very expensive. Regardless of the technology, they're just very expensive devices, because it's difficult to design the electronics to give you that sort of resolution. So, what are the rules about this? Well, let's just consider simple measurements, a couple of rulers. Now, taking just a single ruler, these are two slightly different scales. If we operate over the same distance, let's go from there to there, we can see that with the finer scale, the finer resolution, we've got more lines. Whereas with the coarser resolution, we have fewer lines. The actual range we're operating over, the total operating range is the same in both cases. But if we have a finer resolution, we need more lines. This is logic, this is straightforward common sense. And the same is true for an ADC. The finer the resolution, the smaller the minimum resolvable value. And here we have a minimum resolvable value here of a millimeter. The smaller the resolvable value, then the more bits we require to describe that conversion. So there must be a relationship between the total bits is clearly proportional to 1 over the minimum resolvable value. We'll go back to, we'll add this to our other equation in a minute. Why is that? Because the smaller our resolvable value, the more bits we require in our conversion. So there is this relationship. But there's another factor we have to take into account. One other factor. Go back to our ruler. We know that the number of bits is related to the inverse of the minimum resolvable value. However, it's also dependent upon the total range. If we're only operating over that range, we have only, well, this is a millimeter scale, we have only 50 bits there. However, if we were to double the range, we need more bits. Again, a lot of this subject is just pure common sense. So the other factor that we have to take into account isn't just how fine we want to measure to, but how long the total operating range is. The longer, the larger our range, the more bits we need. So we need to complete this equation by saying the total number of bits is the maximum range divided by the minimum resolvable value. So now I've given you two equations to help you select ADCs, and we'll combine both those rules together. All this information is available from the original system specification. The sampling rate equals the maximum rate of change divided by the minimum resolvable value. Very straightforward, and we did an equation, just repeat it. If we are trying to measure to an accuracy of 10 degrees Celsius and our maximum rate of change is 100 degrees Celsius per second, then the sampling rate must be greater than 100 divided by 10 equals 10 Hertz. That was the example I just gave you. Let's go to the other problem. How many bits? This is the minimum number of bits. It is the total range divided by, again, the minimum resolvable value. So the greater our range, the more bits we need. And the finer our resolution, the more bits we need. So again, let's consider our Bessemer converter that operated over 300 to 1500 degrees Celsius. Therefore, the range is 1200. 1200. And our minimum resolvable value was 10 degrees, so we divide that by 10, we get a value of 120. 2 to the power 7 equals 128. Therefore, the minimum number of bits in our ADC is 7 bits. 7 bits. Two very simple equations. These are key equations that you need to remember. Oh, hello, welcome to the second major lecture on real-time systems development. We've covered now everything you need to know about how to get information out of the real world. The real world has measurands, which we use transducers to convert those values into other measurands, into electrical signals. Those electrical signals, if they're voltages, will go through ADCs into our system, or if they're pulses or frequencies, we'll take them in through I/O ports and we will read those numbers in using software. We then play around with those numbers, take decisions, and now we want to control the outside world. Now, forget about computers. I'm going to show you some more output devices now that you need to know about and that you need to control. First product I'm going to show you again is the engine management system for a car. And the component of particular interest to me are these ones here. These devices here are known as relays. These are very simple electromagnetic devices. This particular winding here, that is connected directly to an output of our computer. The computer, remember, it only understands two levels, a 0 or a 1. When something is true, 1, 5 volts is flowing, that passes a current through the coil and that turns the coil into a magnet. And what happens is that this small contactor is then attracted by the magnetism and changes state. So, by energizing the coil, the connector will move and change the state of the relay. What this means is, and here we have the second relay in the system, what this means is that we can use our computer signal. Here's our computer, very low voltage signal, can energize. It's quite a big coil, so you get a lot of magnetism out of this thing, and it will switch what in fact are here totally independent circuits. These wires at this end of the system here are connected through these connectors. They've got nothing to do with the computer voltages whatsoever. We can put whatever we like on here in total isolation of our computer. Now, why do we need to do that? Consider, why do we need to do that? Computers, low level voltages, 0 and 5 volts. But most things out there that we want to control don't run off low computer level voltages. They run off much higher voltages. A car, 12 volt battery. If it was a truck or a lorry, that would be 24 volts. Most serious machine tools in factories actually run off 24 volts DC. If you were to put 24 volts onto your poor little computer, all that would happen is it wouldn't run, it would just die. It would go up in a puff of blue smoke. Computers cannot drive real systems. There's not enough oomph, there's not enough power in the 5 volt TTL voltage levels of a computer to drive the real world. So we need to interface these voltages to the high level voltages outside. It might not just be DC, it might be the mains supply, 240 volts AC, continuously changing sinusoidal voltages. How can we get a computer to drive those signals? Well, the answer, the simplest answer, are these little relay components. Let's see a bit more detail how they work on the board. Here's our computer output. Now, a computer output, as we know, normal computer voltages is either a logic level 0 or a logic level 1. That is the equivalent of 0 volts and 5 volts. If we connect the other side of our coil down to ground, which is the 0 volt common, when our computer signal is at 0, no current will flow through the relay. When we output a 1, a logic level 1 on our computer, suddenly current will flow, and that current going through the coil generates a magnetic field. And if we have very close to our coil magnetized material, what happens is the magnet pulls the switch shut, and that closes the secondary circuit, which can go off to our factory or our motor, or our system, whatever it is. So if we come back to our small relay, here we have, again, as I've already told you, most microcontrollers, which are the processors we're talking about, the vast majority of these pins are digital I/O, input and output pins, which are memory mapped onto your system and can output directly a logic level 0 or a logic level 1. 2 of them are connected to these relay coils. So if in your program you say that memory mapped bit is equal to a 1, if we set this pin to a 1 by a very simple operation in the program, writing a variable 1 into that memory mapped I/O, that pin suddenly switches from 0 volts to 5 volts. It goes through the coil. The coil is magnetized. This is a magnetic material is sucked down, and that changes the state of the relay. So now this connection here, you notice it's a very thick piece of metal, because this in fact is able to take an extremely high current at very high voltages, will flow, instead of to this connector, it will flow to the other connector, allowing the current to come out a different wire. So the computer signal is able to switch the input voltage. It comes in here. This in fact comes directly from the battery supply, and it's switched out to either that output, or there's no connection there on this one, that output. These are the 2 connections on either side of that relay. So what we are able to do with our simple 5 volt output is to switch much higher voltages, and these are totally independent, so there's no chance of this high voltage frying the computer. It's totally electrically independent because it's been achieved by magnetism. And you can have DC voltages, it could be 5 volts if you wanted to, up to 24 volts typically, usually very high voltages, or it could even be the mains. It's only a wire after all, so if you were to plug that into the main supply, you'd have a 240 volt AC main supply, could be connected off, and that could switch on an AC driven motor or system or light or whatever it is you want to control with the AC mains. So a relay is an extremely simple electromechanical component that's used to interface a low-level computer output signal to some instrument or system that runs off a very high DC voltage or an AC voltage. Very, very simple concept. Electromagnets are very useful devices, very clever. The nice thing about magnetism is it's electrically independent. It means our computer can have its own clean 5-volt power supply, and using magnetism it can then make things happen externally mechanically. Why mechanically? Because most things we want to happen in the real world are mechanical things. We want to move things about or switch a motor on which then rotates, or a paddle wheel. Mechanical movement is extremely useful. So I want to introduce to you another very interesting and useful electromagnetic component. And this device is known as a solenoid. Now how does that work? Again, it uses magnetism. And if we have, again, our computer output goes to a magnetic coil, take one side of it to 0 volts, and the other side is our computer output signal. Remember, that can be a 0 or a logic level 1, and logic level 1 is 5 volts, and that's 0 volts. When this is set to a 1, which you just do by writing a 1 to the particular memory location that this output port has been mapped to, current will flow through the electromagnet. Magnetic theory tells us that if we place in the middle of the coil a ferrite core, a permanent magnet, when this becomes magnetized, let's assume that's a north pole and that's a south pole, and that was a permanent bar magnet, and if we put it in, so that was the north pole and that was the south pole, as soon as that's switched on, the rod is fired out of the coil by the magnetic effect. And this process is known as a solenoid. And if you don't believe me, I'll show you one. So we have one here on the bench. If we move it to the scanner, you might get a better view. Now, I've removed this particular solenoid. This, in fact, is the valve that controls the flow of water. Do you remember this component from the previous lecture? This is the part of the mechanism of our electric shower. I did tell you it was a very complicated thing, an electric shower. This was the sensor I showed you yesterday with a little turbine wheel. Here's where the water flows in, goes through the turbine wheel and then comes out. This was the valve that sat in here and controlled the flow of water. How did it do that? Well, it did it by simply pushing a barrier in the way of the water. This here is the valve. The valve sat in there like that, and you might just make out I can push that valve in and out. And as the valve moves in and out, just like the washer in your own sink at home, as that rubber bung moves in and out, so it stops the flow of water or lets water flow. How did that operate? Well, here we have this plunger arrangement. Here, hopefully you can see the plunger. As the plunger moves in or out, that will push the valve in and out, so that stops all the water flowing, and when it's fully in, actually depressed in like that, it has to be sucked in, then that lets full water flow, and there's actually a small spring in here. You might be able to see the spring compressing. That is the restoring force on this particular mechanism. Here is my coil. This is the solenoid. It slips into there with the spring, forcing it in and out. That's pushing this valve arrangement in and out. That's letting the water flow. That's blocking the water off. Let me show you how this works. What happened? What did you see? Now, what I'm going to do is, at the moment we have the valve is at the moment pushed fully out on the spring, So that means that in the rest position, when the shower is off, the water will not flow. But we need to suck it in. In order to suck it in, we apply the voltage. All we do is we're switching on a computer output and it goes, it's sucked it in. Now all that you've done is one line of program code has pulled it in. It's just output a logic level 1 to the coil, and as soon as we release it, away it goes, because the spring gives you a spring return, thereby closing off the valve again. So let's run through that again. Very simple system. Here's the coil, solenoid, that is connected directly, just by one side goes to ground, one side goes to ground, the other side is going to a computer output. The computer is actually buried inside the shower system. I haven't been able to get it out. We put that mechanism in here. This mechanism, there's the solenoid with a spring return. In its normal rest position, the valve is fully out. You can just see that we have the valve here is fully out, and that will stop the water flowing. In order to let the water flow, we need to pull it in, and that lets the water flow through this area and out into the rest of the shower system. So let's just switch it on again. So we want to turn on our shower, we want to release the water. Pull the valve in, release the valve out, and away it goes. Now of course it wouldn't shoot off across the bathroom floor because it would be trapped inside here, but that is the normal rest position, will stop the water flowing and dripping down through the shower mechanism. There we have an extremely simple demonstration of a solenoid. So let's return to our drawing of the solenoid. We have here a coil with a rod in the middle, goes straight to a computer output. When we energize the coil, it's pushed out. When we release it, well, unless there's a spring to push it back, it will just stay where it is. So most solenoids also have this extra mechanical component, which is just a very simple little spring, and it presses against the spring when it's forced out by the computer, and that gives you the releasing force. When you switch the computer off, it goes back to its rest position. That's a solenoid. Wonderful things, solenoids. Let's think what else we can do with them. Here's our two wires back to our computer. Very simple. One goes to the computer, one to the ground return. Here's the coil. Here's our rod. There's our rod. So we have a mechanism now. Using a computer, we can move something mechanical in a linear direction. Now we've seen how that can be used to control the flow of water in a shower simply by moving this solenoid in and out to let small amounts of water to flow through. It could do other things, couldn't it? It could actually engage mechanical components. Have you ever wondered, when you've seen a machine tool, have you ever seen one, how do you get these moving parts to move backwards and forwards? Well, more often than not, it will simply be a solenoid movement pulling a metal component in a linear direction. You could put a lever arrangement here, couldn't you? A fulcrum, and as that pushes out, it rotates, so you can get rotational motion. And when you design a real-time system in partnership with a mechanical designer, and you normally do this, you normally have a team of an electronics engineer, a software engineer, a real-time software engineer, I must stress, a mechanical designer, optical designer perhaps, machine tool designer. You work as a team together, and you can create the most clever pieces of miniature robotics and even large robotics using simple lever arrangements and an arrangement of solenoids. But let's do something even more interesting. Here's my rod. Why don't I also insert into the rod a slot? we drill a hole right down through the middle of it. And let's assume this in fact is a pipe, some form of pipe work. And we could have a fluid flowing through that pipe. In order to switch the fluid flow on, if we engage our solenoid, the hole will move to that position and allow the liquid to flow. And when you want to stop the liquid flowing, you pull it back. So what? So what's so exciting about that? What could that fluid be? Well, it could be petrol. So we have the basis of a fuel injection engine. It could be oil, providing lubricants to various parts of the machinery. It could be gas, switching on and off the gas supply to a burner. And most important, it could be air, because believe it or not, the most popular fuel used in industry today isn't oil or gas or petrol, it's air, high pressure air. Pressurized pipes are laid around factories, and we have pneumatically operated industrial instrumentation. A lot of robots are in fact based on pneumatics, not electrical motors at all. And the pneumatics are controlled by switching on or off air supplies to actuators. Actuator is a word for a moving part, and the air pressure forces the pistons to move in and out. So really we've not come much further from the steam engine of the last century. Pneumatics will be found in all modern machine tools, controlled by little computers switching 5 volts through solenoids can switch on and off vast, powerful air supplies. Now, I want to show you a trick, an interesting trick, because the solenoid, as far as we've seen so far, can either switch something on or off. If we have our little valve here, we've seen we can have it off or on, off or on, fully off and out. But notice there is a finite period of time taken before it reaches its rest position. That's because of the strength of the spring. So what happens if I switch it on and it's slowly moving in, but then I switch it off before it's got there, so it starts moving back out. But then very quickly I'll switch it back on again. But before it's reached that end point, I stop, and so it wobbles about. It's never quite sure whether it's fully in or fully out. To put it in a more abrupt manner, think what's happened. Think of me as the solenoid, and I'm moving along, and suddenly the power's switched off, so I'm forced back. But before I had a chance to get all the way back again, I'm switched on again. And what happens is I just don't know where to go. And eventually I'll say, I think I want to be round about here, a rest position in the middle of fully on or fully off. This is a very powerful tool. And it's a process that's known as pulsed width modulation, or PWM. Instead of outputting a fully on signal, let's assume that was our fully on signal, or a fully off signal, what would happen if we go on for half the time and off for half the time, and then on and then off? If we have a 50% mark space ratio, and we do it very fast, this is the key. The spring moved very slowly, but if we fire out these control signals so fast it can't respond quick enough, you have to be at least 1,000 times faster than the response time. The poor old solenoid dithers and eventually reaches a rest point in the middle, precisely halfway. So what we have the ability to do with pulse width modulation is it's not just to switch a solenoid fully open or fully closed, but to precisely position it anywhere within its travel. Let's put up some more graphs. We're discussing PWM. 100% pulse width modulation means that for all of the time period, it's fully on, and that will fully open our valve. 0% pulse width modulation means that it is always off. What would happen if we had it on for 75% of the time? 3/4 of the time on, 1/4 of the time off. 3/4 on, 1/4 off. 3/4 on, 1/4 off. If you did that extremely quickly, far, far faster than the rate of response of the spring, what happens is our solenoid moves to the 75% position, 3/4 open. It does work. 50%. Equal mark space ratio. That would get us halfway. 25%. That would get us 1/4 of the way. Now I must stress this has got to run extremely fast. Now, going back to the original solenoid I had here for the actual motor, control the flow of water, very, very slow motion there. We actually drive this at a PWM repetition rate of 32 kilohertz. That means that the repetition rate here of the cycle is 32,000 times a second. The PWM repetition rate must always be a constant. And what you do is you vary within that how much of it is a mark and how much of it is a space. But the actual repetition rate must be constant for this to work. And in our case, with this solenoid, we drive this at 32 kilohertz, and we have proven in the laboratory that we are positioning this solenoid to within 3 microns. 3 microns. That is an incredible accuracy for what is an extremely low-cost valve. This valve costs about $1 million to manufacture, the whole thing. And yet we can position it to an accuracy of 3 microns using a high-speed processor outputting PWM at 32 kilohertz. Now I have another demonstration of pulse width modulation, which I'll bring over to the bench, and hopefully you might be able to view it. Now, it's a bit fragile. We'll try and get it over to the other camera. I want you to concentrate on the colour of the lights. The colour of the lights. And just tape it down so it doesn't move. Now I want you to look very carefully at the LEDs. And these LEDs at the moment they're bicolour LEDs. They only do 2 colours. They're either red or they are green. That is a green. I know it doesn't look very good on the camera, but they're either red or they're green. Watch what happens as I change the PWM rate between full red coming through oranges. We've got nice orange colours now, so eventually we get down to the green colour. So we can have green going through various shades of oranges, yellows and oranges, eventually coming to full red. Now how is it we're managing to achieve such an incredible range of colours with an LED, when we know that an LED is a fixed colour? Well, in fact, we're using pulse width modulation, and we're relying on the fact that the retina of the eye's response time is round about 10 to 20 milliseconds. And what we're doing is we are flashing alternately the green colour and the red colour at different ratios. Very, very fast, incredibly fast, faster than your eye is able to detect the colour. So that as we change the ratio of the mark space ratio and the PWM, so it appears to our eye that we have an orange colour round about the middle as the two colours mix together in our retina. And there we have, I can assure you these are just two colour LEDs, green at one end, red at the other, with a varying spectrum. So enough of that demonstration, let's discuss what we've seen. This was another example. Actually, if you want to know, this is in fact the controller from a spin dryer. Ordinary clothes spin dryer from a laundry. And the way we did that was as pulse width modulation. It really does work. You've seen two examples now. You've seen it with a solenoid, you've seen it with a pair of lights. With a single digital output, as long as you have a constant rate of change, the PWM rate must be a constant, and we vary the mark space ratio. There's something that's almost fully on, varying through, say, 50%, well, not quite, 50% on, 25% on, down to almost fully off. Remember, this repetition rate must be extremely high, extremely fast, and what happens is we fool the thing we're looking at, we're working. The time constant of whatever it is being driven by these signals must be substantially slower than repetition rate. And the end result is that these very high changing frequencies get spurred out, gets mixed together into a variable analog signal. And so what we have is the ability to get a computer to mimic a variable output signal. Thus you saw the green LEDs and the red LEDs together merging to give us a sort of orange colour. And similarly with our solenoid, we can position the solenoid to any position we like within the movement range, the dynamic range of the system. So that is pulse width modulation. We've examined relays, we've examined solenoids. These were mechanical components. They work very well, but the problem with them is any mechanical component will wear out. There's nothing we can do about this. Mechanical components do die. So for systems where there are thousands of changes an hour, very fast systems, a lot of switching, you can't use mechanical components. So we've got no choice, we have to use electronics. Electronic components do cost more than mechanical components at the moment. But we do tend to use them where we have to have some high-speed switching. So I'm going to introduce a few of them to you. One of the nicest types of device uses light. Now we already know that if we put a current through an LED, it outputs light. So here we have, here's our LED, light emitting diode. We know, I mean, you get LEDs all over the place, all over your computer telling you the disk drive is on. All it is, it's a directly driven computer signal. You can drive these directly from a processor output. You switch on the light, and we switch on current through the LED, and we know it sends out light. Now, in science, if one transfer of energy is possible, the opposite transfer can also be achieved. And that means that if we can force current through some semiconductor and it generates light, we must also be able to shine light onto the device itself, and it internally generates the reverse current. And these devices are known as photodiodes or phototransistors. If we have one of these in our circuit as well, this device here is our diode. When a current flows through the diode, light is emitted. Here we have our photodetector. In this case, I've drawn a phototransistor. When light falls onto the base of the transistor switches on and current is allowed to flow. So this means instead of using magnetism to transfer our on-off state from our computer to the external device, we use light, we use a photon. A photon will cross over from the diode to the detector. If we seal the whole thing up into a capsule so no stray light from the outside world can get in, we now have the design of an optocoupler, sometimes also referred to as an opto-isolator, or for obvious reasons, an opto switch. All it is an optically coupled device whereby when our computer switches on the LED, that photon or the photons will switch on the phototransistor and will allow current to flow through the device to some external device. Now they only work with DC. That means we can only have the current flowing in one direction. So you can use them to switch on a 12-volt supply or a 24-volt supply. So you can use optocouplers to switch on high DC voltage equipment externally to the computer. Very, very nice too, because what it means is that your computer signal, just ones and noughts, output to memory mapped I/O, switches on these optocouplers. The optocouplers then optically enable the other side of the switch where very high currents and high voltages, plant supply voltages can operate, and that will then switch on or off the machinery you want to control. Another example, totally trivial example, the remote control for a television. How does that work? Well, in that case you have an infrared LED, you point it at the television, you press a button, and out go pulses of infrared light. And they're transmitted over a distance, and you have an infrared optical receiver in the television, which is in fact no more than a phototransistor that is tuned to the infrared bandwidth of light, and that's what puts the pulses, the signals into your television, and you can change the channel. Same concept, it's an optocoupler. It's just that it's using it as a transmission link. And that's another way of using these things. You can actually use infrared links from a computer to control a piece of machinery over a distance, and that means you can have your computer control in a nice clean environment, and you can have your machinery remotely from it, and you switch it on and off just like a television. Very, very nice system. So you need to know about optocouplers, opto-isolators, opto-switches, whatever you care to call them. Low voltages on one side, optically coupled will switch a high voltage on the other side. Now let's have a brief review of the devices I've shown you so far and think about what they can change, what they can switch. We have a relay. Now a relay, that's mechanical, and it uses magnetism. It's a magnet. What can it switch? It can switch DC, batteries, 12 volts, 24 volts, and AC. Because it is electrically isolated, you can switch on anything you like through the relay. Let's look at our relay from our car again, and we'll see that is so. Here is our relay. Here's the wires. Here's one where all three sides are wired up here. Three totally independent contacts. As that switches, it changes state, and these wires could be, well, in this case it would go to the car battery, but that could be the AC mains, a variable voltage signal rather than a direct current. So these relays can be used for AC and DC. Solenoids, again, they're mechanical, they're magnetic. They're usually used to either switch an air supply or a fuel supply, or alternatively they may themselves be the mechanical movement. And don't forget, PWM, very powerful tool for positioning a solenoid in any position you like. You can't do that with a relay. If you did, the relay would burn out very quickly, but you can do it with a solenoid. Optocouplers and isolators, these are electronic. They use light. They can only switch DC, 12 or 24 volts, that's all. You could PWM them, but they tend not to be fast enough. The transistors change state too slowly for that to work properly. I have seen it attempted. In fact, the demo I showed you is PWM of LEDs. And so in some circumstances you can use PWM, but it isn't always that perfect. But how are we going to switch the mains voltage? The problem with an opto-isolator, because the mains changes state, going positive, negative at 50 times a second, 50 hertz mains, 240 volts in your country as well as here, how is it we can control the mains? Because the optocoupler will only allow current to flow in one direction. So let's think about this. Let's draw our mains and think about what happens. If we have here our mains voltage, this is a 50 hertz cycle, plus or minus, well, it's actually 240 volts AC, peaking at about 320 volts. Because the optocoupler will only allow current to flow in the positive direction, only half the mains cycle would get through the phototransistor. All of the negative part of the AC would be lost. So we need another technique. We need another type of mechanism to switch on the mains. That particular device, quite an important one in real-time systems, is called a triac. What a triac is, don't worry about the electronics, that's not part of the module. I'm just doing it for the sake of completeness, but this, I wouldn't examine you on the solid state electronics of this, that would be grossly unfair. But this is what the device looks like. It's a pair of back-to-back diodes. And that means that normally the voltage from the AC mains is blocked in both directions. Both these diodes tend to block any movement of current. But the interesting thing about them is that even though that's 240 volts AC, all you have to do is put a tiny little bit of energy injected into the diode pair, and the diodes break down and current starts flowing. And as soon as a little trigger pulse switches the device on, it stays stuck on. So what happens is you have your triac, that's there, that can cope with the mains voltage, 240 volt mains. It's normally off because of this back-to-back diode arrangement, blocks all the current. But a tiny little bit of energy, believe it or not, 5 volts, that's enough, a little pulse of energy, the avalanche effect in the triac, it breaks down and the AC mains can suddenly pass. So we could use a triac to switch on and off the mains. So let's think about how we'd do that. 240 volts AC going off to some, I don't know, hefty motor somewhere. If we were to take that directly to a computer signal, all we have to do to switch on the mains, raise that to 5 volts, and for all the time that the signal is true at a logic level 1, the mains is off. So we can, effectively a TRIAC is a solid state and electronics mains switch, just like the switch on the wall, but it can be controlled directly from a computer signal. Now I have to say, in terms of design, I would be a bit wary of this. If this was to short out accidentally, you could get a 240 volt main spike going into your computer and it will burn out your computer. You won't like that. So in fact what we do is we combine together. Here's our computer signal. Normally I would put that through an optocoupler, combine them together. This is only so I've got the electrical isolation, and then I would feed that signal into the TRIAC, and then I would let the AC mains pass. So what you do is a small computer pulse there. We know when that's on, that is on. When that is on, then the main supply is switched on, and so we can use a computer signal through an opto isolator, and now we're using it in its isolation mode. The opto isolator will switch on the main supply and will switch on our motor. And if there's any damage occurs in here, this component breaks down or burns up, because there's no electrical contact there, our computer is protected. That's the safest way to do it. So using an optocoupler connected to a TRIAC, we can control the mains. Now I want to show you a trick. When you switch a TRIAC on, it stays on by itself. As soon as you've broken down the diode, if the little 5 volt signal from your computer can break it down, you can be sure the 240 volt mains will keep it broken down forever. But the thing about mains is it changes state 50 times a second. So that means every now and again, in fact 100 times a second with 50 Hertz mains, the AC voltage actually goes away momentarily, it disappears. Now if it's gone to 0 and the computer signal is no longer present, the TRIAC switches off again. So let's think about what happens. Here's our voltage. That's the input to the TRIAC. Let's assume we do a small pulse from our computer just there. That will switch on the mains and it will flow for the whole of that cycle. But if we remove our computer signal immediately, so instead of just holding it on, we do a very short pulse and then we take it away. At that point, when the mains goes through what's called the zero crossing, at that point here, the main has gone to 0 volts, just as it's changing from positive to negative. Our computer signal's gone away, our TRIAC will switch off. So in fact, what we've done is that we've output a single half cycle only. So if we wanted to pulse our TRIAC and we wanted the next half cycle, we'd have to put another short little pulse there to bring it on for that half cycle. And then if we wanted to keep it on here, we would have to pulse it again. What would happen if instead of pulsing at the beginning of each cycle, we pulsed it in the middle? Now we know that while there's no computer signal, the TRIAC is off. That means up to this point in time there is no output voltage. if we now put our little computer pulse in the middle, suddenly the triac switches on, but halfway through the mains. And it will stay on until it reaches its zero crossing, at which point it goes off again. And because there's no computer signal, it stays off. What happens if we put a pulse in the middle again? There. Suddenly, it will come on again. And so on for the next half cycle. At this point, it will come off. If we put another pulse there, it stays off, and then suddenly it comes on and goes off again. So what we have is a mechanism, is that here's our AC. If we change the point within the cycle where we spark the triac on, we can actually adjust the amount of AC that is allowed to pass. So what we're doing is we're using the computer to control the amount of voltage that passes. Now you'll find this in your notes. If you just turn on a few pages, hopefully you have the books, and if you get this up, you won't see it over the camera, but please turn to this page for this section of the discussion. Here we see the AC mains, the pulses in and out of phase. Here we have 50% mains being allowed to pass. Here we have a very small part, about 20 to 30% being allowed to pass, by moving the point with respect to the cycle where we pulse the triac on. So what we have here is the means to vary the AC voltage that's allowed to pass. Now you may or may not have come across these in the past, but if any of you have ever used a dimmer switch for room lighting, that's exactly how they work. When you go to a normal room light and you switch it on, all of the mains is allowed to pass. But if you've got a dial underneath to dim it, what the dimmer does is that it actually has a triac in the switch, and it fires the triac on at different points in the phase cycle of the AC mains, thereby dimming the light. That's exactly how the motor, I showed you the motor in the first lecture, and what we might do is try and get this thing working again, but this particular mechanism uses phase modulation to control the speed of the motor. I've packed it all up, so the chances are it's not going to work a second time, but let's have a go, you never know. Sometimes these demos work more than once. Leave it. Let's see what will happen. Now, even though you can't see the motor that well, you can certainly hear it. This is it with the phase modulation at a very low rate. And here I have a phase adjust knob, and as I move the phase from nearly 90 degrees out of phase, I can vary the speed of the motor under computer control That has all been done with phase modulation. Here we have the computer, just to prove to you it is computer controlled. The triac is here, because I don't want it very close to my computer. There is the computer signal going in to here. This component is a combined triac with an optocoupler. This is just a 5 volt signal goes in, and there, that is the main supply comes out. So the computer signal directly from the processor, here we have the processor output is directly controlling the TRIAC input, and that is switching the mains. And as you heard, even though I know you can't see it very well, as you heard, I was able to vary over a very wide range the speed of this AC motor using a little computer that cost 90 pence. A very, very low cost device. Because of course all domestic products have to be low cost. So this is another shower. I think I showed you this in the previous lecture. So that is how we control the AC mains using phase modulation. So you've been introduced now to two forms of modulation, and you need to understand the difference between the two. You need to understand the difference between pulsed width modulation and phase modulation. Diagrams in the notes. Pulsed width modulation, it's a DC concept. We either have a thing fully open or fully closed, and by varying the mark space ratio of the DC output, we can position our solenoid or the appearance of our LED to be anywhere we like within the full range, from fully open to fully closed. Phase modulation is used to change the point in the cycle of the AC mains where we trigger the AC voltage. So if we trigger it near the beginning of the cycle, we get nearly the full power of the mains. That is a zero phase shift. The more we move the phase with respect to the AC signal, when we hit 180 degrees phase shift, then we would get no mains whatsoever pass through our system, and would get no voltages passed. Now I'll tell you a story. One of the more entertaining products I had to design many years ago was a system for measuring the water vapor transmission rate of packaging material for food. Now this is quite important. If you've got a product like butter, it's quite important when it's wrapped that moisture doesn't escape. Whereas there's other components, other materials, it's quite important we do let water in and out. So the rate at which water is transmitted through wrapping material is quite crucial for the quality of the goods you want to put on the supermarket shelf. And what we had to do is we took a sample of the paper and we put it into an environmental chamber. We had to maintain it at a constant temperature while we measured how much moisture passed from one side of the piece of paper to the other side of the piece of paper. Now, environmental chambers are extremely expensive devices. How did we do it? We did it with a light bulb. We took an ordinary domestic light bulb, we put it into a bulb holder inside a metal box, and using phase modulation we varied the amount of output from the light, because no matter how good the light is, as you know, there's always some little bit of heat. There's output from a light bulb that's switched on. And by effectively we had a dimmer circuit. When the light was on a very, very low dim, we had a very little amount of heat coming out. If we wanted more heat, we just increased the brightness of the light bulb using phase modulation, and there we had an extremely low cost but extremely accurate environmental chamber. So that's relays, solenoids, optocouplers, triacs, and we've also discussed phase modulation and pulsed width modulation.